Thank you very much. I'm going to try and not move around too much because of the microphone here. Okay, yeah, I'm Anna, and my talk is going to be about applying automatic speech recognition technologies to singing. This is basically the topic of my PhD project, which I'm planning to finish in the next couple of months. So I'm going to be talking about what I've been doing for the past 5 years, more or less. And just to start you off, before I became a PhD student at the institute, I also did my diploma thesis at the same institute. And that diploma thesis was about classifying world music into the region of origin. So I was trying to develop features and write classifiers to, for example, classify Indian music versus South American music, that sort of thing. The results you see down here, I don't know how well you can read them, but those aren't the results of my classifier. Those were actually much better. These are results from a listening test where I asked people to tell me what they thought where songs came from. And those are non-experts, obviously, but you can see those really aren't very good results. One very interesting thing that happened during that listening test was that a lot of people, without being prompted, told me that they just listened to the language. And that was something that I didn't take into account in my classifier at all. And that got me thinking maybe I should take that into account. If people are just listening to the language, then maybe the model should listen to the language too. And then about a year later, we had a project at the institute that was about finding music for TV commercials. And this is apparently a typical request that music labels get when advertisement studios are looking for music for a commercial. So they get a request like, we need a song that is slow, it has to have a certain instrument in it, we need a specific drum pattern, must be a male singer, we want a specific style or a specific mood, and then it also has to be in a certain language and it should have this special word in it. And I guess you're all from MIR in some way, so you know that a lot of these things may not exactly be solved, but at least there are people working on them, except for those last 2 points. So when I started my PhD, there was no one who could tell you that a certain song was in English, or that it has a certain word in it, and that's what gave me the idea to start looking into these problems. So in this talk, I'm going to be talking about 4 different tasks that I've worked on. I'm going to be first talking about phoneme recognition a little bit, because this is the basis for almost all of the other tasks that I've worked on. And then I'll tell you how I applied this to language identification, keyword spotting, and lastly, lyrics to singing alignment. Now you might ask, why do you even want to do that? We already have ASR technologies. ASR has been a topic of research for 30 years or more. Why can't we just apply this to singing? And as you can probably imagine, singing has a lot of characteristics that are very different from speech, and that includes larger pitch fluctuations. The pronunciation can be very different and even can vary in one speaker. The timing is very different from speech, and it varies more. We've got different vocabulary than, say, someone reading the news on TV. And then, of course, one of the biggest problems is background noise, or background music, as you would call it then. Although I'm not going to be talking much about background music, because most of my work so far has been focused on a cappella singing, just as a starting point. Okay, so I said I'm going to be talking about phoneme recognition. That's what I'll get started on. This is a small overview of the state of the art of phoneme recognition in singing, and this is pretty much complete. So as you can see, there hasn't been a lot of work done on this task. And one thing that you can also see is that people can't really agree on what exactly they're evaluating. So we've got approaches that try to recognize 40 phonemes, which like 39 or 40 phonemes are very common for English language speech to use. But then some people reduced it down to 27, and some people just looked at vowels, or just like 15 general classes of phonemes, which of course makes it very hard to compare. And on top of that, people also use different evaluation measures for all of this. So some people look at the frame-wise accuracy. Some people use measures like the phoneme recognition rate, but they also do it in different ways. Some just use recall, so that makes it very hard to compare whatever you're doing to this, or even just to compare them to each other. And of course, everyone's working on different data sets. Okay, so when I first got started on this, I ran a baseline training, and this is basically just taking timid, which is one of the most widely used speech recognition data sets in English language, contains 4,600 hand-annotated utterances. So someone sat down and said, okay, this phoneme goes from here to here. It's just speech, it's pretty good quality, and yeah, everyone uses it. Maybe you've seen it. Oh yeah, that's it. Sorry, I forgot there was an example in here. I'm going to play that again, so this is what it sounds like.
She had your duck suit and greasy wash for all year.
Yeah, that's one utterance in timid. And then I thought maybe this doesn't sound enough like singing. So one of the things I did maybe 2 or 3 years ago was to modify timid in a way where I thought that would make it more like singing. And the way I did it was by introducing pitch shifting, time stretching, and vibrato, which I generated artificially. Pitch shifting was done on whole words, because that's what you would commonly do in singing. But time stretching was just done on vowels, and vibrato was also just done on vowels. And I think there's another example here. So someone told me it sounds kind of like drunk singing. It doesn't really sound like singing, but the idea was to maybe make it a little bit more like that for training.
She had your dog sick and greasy, washed water all year.
Yeah, so that's what that sounded like. And then I basically went through the standard machine learning procedure, what you would do with these two data sets. So I have here the timid training data set. Can you read this? Is that okay? Not that I could change it now, but yeah. And then I did these modifications that I just mentioned, and to be able to compare it, I did that in several different configurations. I extracted MFCCs from that, and then I trained different models on that. And yeah, so in that case, I trained DBNs and DNNs, and that gave me a couple of different models to compare. And with those models, again, I was able to recognize phonemes on unseen data in the same way. And yeah, if you've never seen any output of a system like this, so what I usually work on are phoneme posteriograms, and this is more or less a matrix which tells you at each frame how likely each phoneme is, right? That's what the model tells you, the phoneme probabilities for each frame. Okay, so this is one of my results. This is a comparison of the modified data that I showed you compared to just the standard timid data. And this is the percentage of correct frames, which is a very strict evaluation measure, I guess. And the blue bar here is just models trained on standard timid. And the other colored bars are those modified data sets that where I just played the example. And interestingly enough, it turns out if you modify the pitch on that, it doesn't help you. My interpretation of that is that since I'm extracting MFCCs, those are supposed to be robust to pitch. And it turns out that in this example, at least, it doesn't change anything if you change the pitch. Whereas if you do time stretching on your vowels, then it actually improves the results a little bit. So this was done on a singing data set, and then I also tried the same thing on a different subset of timid, which wasn't included in the training data, and what happened was what you'd expect, that it actually got worse on speech data. So that's a nice result in that regard, that you see that it actually gets better when you train models on this modified data and then test it on singing, whereas if you test it on speech, it gets worse because it just does something to your data that wouldn't happen realistically in speech. And this is just a different evaluation measure, so that's phoneme error rate, which means lower is better, and you can see the same trends here, more or less. Okay, so then one thing I really wanted to do, even before I got started on that experiment, was to use actual singing data for training. But as you probably know, it's really hard to get that sort of data set anywhere. And it took me a long time to find one that would work for my purposes. And I just got very lucky about 2 years ago when I heard about this damp singing data set, which is freely available. And that contains 34,000 recordings from a karaoke app. So it's amateur singing. The musical quality is debatable, I guess, but the audio quality is usually very good. It's recorded on mobile devices, and those seem to have pretty good microphones most of the time. There's no background music. People usually sing what they're expected to sing. And the one thing is that this dataset still doesn't have annotated phonemes. But since it's from a karaoke app, the lyrics are available online, so you can get those lyrics from the website of Sing, and that's what I did. And then I took those lyrics and the audio recordings and ran my automatic alignment on that. I'm going to be talking a little more about that later. And I did that for 6,000 recordings, which is a nice big data set that you can use for lots of purposes, I think. And I have an example of that here too.
So this is what you meant when you said that you were spent. And now it's time to bow from the bottom of the pit right to the top. Don't hold back.
Yeah. So that's what it sounds like. Yeah, maybe I'll show you what the alignment looks like right now, because I have that here. So I hope you can see this. So this is probably not easy to read, but if you look down here, I'll also show you the phoneme, as you probably know. So that's the same sound example, and then on the bottom right you can hopefully see the phoneme a little bit. And I'll just play this. Okay, maybe a little bit cooler.
When you said that you were spent, and now it's time to bow from the bottom of the pit right to the top. Don't hold back. Packing my bags and giving the academy a rain check.
Okay, were you able to see that? So, and that's a realistic example, so I didn't do any manual modifications on that. Let's go back to this. So once again, this is the process that I ran through with that. So I have my sung audio data, I have the text lyrics that I got online. And then I do my alignment, and I do that using acoustic models that I had already lying around, which were again trained on Timid, in just the unmodified version of Timid. And that then gives me an alignment of my singing and the lyrics. And I again split that up into a training set and a test data set, ran my new training with that. And at that point, I basically forgot about all of the acoustic models I had before that and just trained on this aligned data. And that gave me new acoustic models, which I can again then use to recognize phonemes on unseen data. And it turns out that that actually works much better than training on just Timid. So this is again the percentage of correct frames, or frame-wise accuracy. This is the same blue bar we've seen earlier, which is for models just trained on Timid. This is one of the modifications that I showed you earlier, and these are models that were trained on this new aligned data set. So you can see, even though the alignment might make mistakes sometimes, it'll still give you new data that is useful for training these new models. Yes, and this again is the other evaluation measure, and you can see the same trend that the phoneme error rate goes down a lot if you use models that are trained on actual singing. It's a nice result. Okay, so that's the part for phoneme recognition so far. Now I'm going to be talking about language identification. And I just want to mention that I actually did most of that work before the phoneme recognition stuff. So I hope that we can still put that together. Again, this is an overview of the state of the art for language identification and singing. And again, this is a complete overview as far as I know. So this is another task where people haven't done a lot of work, and also another task where people are using different data sets, and it just happens all the time. People work on even different amounts of languages. At least the evaluation measures here are the same, more or less, so everyone's using document-wise accuracy for language identification. But still, yeah, we've got different numbers of languages, and it turns out that your results actually, even if you're comparing two different languages, it depends very much what languages you're comparing. Okay. And since we again have all these legal problems with those data sets, I actually asked a couple of people about their data sets, and they either don't have them anymore or they're not allowed to publish them. So I had to make my own data set, which, okay, maybe I should first mention that I also have speech data for comparison, because there are speech data sets for this sort of thing around, and they're public. And then my own data set consists of audio that I've downloaded from YouTube. So I went on YouTube and I looked for people singing something just by themselves in 3 different languages. So I've got recordings in English, German, and in Spanish. And I'm going to play an example again. Okay, that's enough. So you can already hear that this was not very good quality, and as you can imagine, since it's taken from YouTube, the quality varies a lot between those examples. Some of them have some background music, or not background music, but background noise, or some very different recording conditions. Okay, and then the approach I tried out at first for this, oh, sorry, it's not the first one, but this is the best working approach so far, and that's based on I-vector extraction. I don't know if you've heard of that. I'm not going to go into too much detail because it's a pretty involved process. But this basically doesn't build on top of what I mentioned before, so this doesn't do any phoneme recognition. Instead, it just takes the audio data, and then I tried different features that I commonly use, ran them through my I-vector extraction, which is basically a post-processing step on top of the features. And then I trained models on those I-vectors, and I tried MLPs and I tried SVMs. So this was a couple of years ago. By now I probably would train different models on that. Yeah, and maybe I should just say I-vectors come from speech recognition, and they were originally used for speaker identification, and they've now been very successfully used for other tasks like speaker verification and obviously also language identification in speech itself. So yeah, if you're interested in that, yeah, I'm not going to talk about the details here, but if you're interested, just come ask me or read up on it. Yes, so it turns out that I-vectors also work very well on singing. So again, the blue bars here are the results on singing if I don't do I-vector processing, and this is just, again, document-wise accuracy for those 3 languages. And the blue bars are the non-processed results, so it doesn't work very well on singing. But as soon as I use I-vector processing for that, it actually goes up to almost 80% here in the best example. And that's on this noisy YouTube data, so I guess if you had cleaner data or a more restricted data set, then that could get even higher. Yes. So that's the first approach I tried out. And then this year I had all these results with my new phoneme recognition models, which is what I showed you earlier. So I had this idea that if I know something about the phonemes in a song, that'll also tell me something about the language, right? And I just very quickly tried out this approach, which, okay, I'll just go through this. So I have my singing recordings, and then I do the process that I showed you earlier, where I do feature extraction and then do my phoneme recognition with the same acoustic models that I mentioned earlier. That'll give me these phoneme posteriograms, which is the matrix that I showed. And what I did then was to calculate statistics on those phoneme posteriograms. And obviously you need pretty long time frames for that, but usually since we're looking at whole songs, that's long enough. So you probably couldn't do it for a recording that's just a couple of seconds long, but if you have a whole song, that'll give you an idea of the distribution of the phonemes. And then again, I used those statistics to train new models, and in that case it was, I think, just a small SVM because it's not a lot of data, there's not a lot to model in that case. And then I tried to recognize the languages from that information. And it turns out that this doesn't work quite as well as the previous approach, but it still works. So I thought that was interesting, and that's actually something I haven't seen done before. So in ASR, people usually operate on a much smaller time scale, so they actually just look at small recordings of maybe one sentence. So no one seems to have tried this out before, but if you have longer recordings, then you can actually find out about the language from the phoneme distributions. And that's so. And what I also want to show with this again is that if I use, okay, let's look at this one. So this is the same evaluation measure as before, and this is again if I use my acoustic models that are trained on speech, and it turns out that for this task the results also become better when I use acoustic models that are trained on singing. So that just tells me that it also works for this. Something very interesting that happened here is that the results also become better for speech if I use models trained on singing. So these are the results on the speech data set that is roughly comparable to this YouTube data set that I mentioned. And in general, the whole task is a bit easier on speech. But what happened was that if I used an acoustic model that was trained on singing, the results also improved as opposed to the model trained on just speech. And I thought that was interesting and maybe something that someone could look into. My explanation for that right now is that maybe if I'm using a model trained on singing that has a bit more variety and maybe is able to better model what happens in the different languages. So yeah, maybe that helps with that. Okay, so that was the second task I wanted to talk about. The next one is keyword spotting. So keyword spotting is this principle, let's say you have a collection of 1,000 songs and you just want to find the ones that contain the word freedom, for example. I don't have a state-of-the-art slide here because no one's doing this. So I was lucky to have a wide open field here. Again, since no one's doing this, there's also no data set for this. So a colleague of mine made one a couple of years ago. And as you can imagine, that's a bit hard to annotate, or it at least takes a lot of work. You can't really do this automatically. You have to have someone sit down and annotate keywords. And what he did was to take 19 English language pop songs, and he just took the vocal tracks from those. We automatically chopped those into 900 segments. And then he annotated all of them with interesting keywords, and more than half of them he also annotated with phonemes. So that's actually the data set that I've run my phoneme recognition experiments on, if you were curious about that, because I have ground truth here. And I think I have an example of that too. So this is, you probably know this one.
Another voice echoing tonight. Cheers only whispers of some quiet conversation. She's
Yeah. Okay. And then on this data set, I just chose a couple of keywords that I thought would be interesting, and that also occur frequently. So I wanted some keywords that occur in more than one song, for example, because if it's just in one song, then the result is very dependent on the pronunciation of that specific singer. So yeah, those are words that you would probably expect in songs. And this is listed by the number of phonemes. I should say number of phonemes here. And one thing I should maybe mention, if you look at the ASR literature for keyword spotting, there are lots of people who don't do keyword spotting for any words with less than 5 phonemes. So this is actually kind of hard to do, even if you look at the ASR literature. Yeah.
So the row with 3, that has 3 phonemes?
Yeah. Did you think 4 because of the 4 letters?
No, I was thinking syllables. I was just
Okay, no, phonemes, yeah. Yeah, okay, so that's where that comes from. Okay, and then when I got started on that, I had a look at the state of the art for keyword spotting and singing, and turns out that a lot of people are using duration information for that sort of thing, because if you look at speech, then if I say the same word over and over again, then my phonemes will usually have roughly the same durations. Even if I start to speak slower, at least the relations between the phoneme durations will remain the same. And my suspicion was that that wouldn't be true for singing. And just to confirm that, I ran this small test on the timid data set and on this annotated a cappella data set, where I just compared the standard deviations of the phoneme durations. And here the blue bars are the results for timid, and the red bars are the results for this a cappella data set. And as you can see, my suspicions were confirmed. So the phoneme durations vary a lot more in singing, and they especially do that for vowels, which is what you'd expect, right? If someone sings a long word, then that will vary more. So So that means I can't use many of the state-of-the-art algorithms, because I can't assume that in singing my phonemes will have the same durations every time someone says a specific word. So what someone recommended me then was to use an approach that is called keyword filler HMMs. And the idea is basically that you have here just a pretty simple, straightforward HMM for your keyword. In this example, the keyword is greasy. You've got two different pronunciation branches here, and then you have another HMM that models everything else. So that's just a continuous loop of that, and that's what I've been using. So again, just to give you an idea of the whole process, let me just check. This one is. Okay, yeah. So you've basically seen this diagram up to here. So this is again, if I'm using my DAMP data set, I have my audio data, I have the textual lyrics, I align those and then train new models on this. And then I can use those models to do phoneme recognition on unseen data. That gives me the phoneme posterograms that I showed you earlier. And then I can try to find my keywords in those posterograms, and that'll tell me where the keywords are. I did that again with the same acoustic models that I talked about at the beginning. This evaluation measure in this case is F1 measure on the whole data set. So I'm trying to figure out how many of those keywords that I'm looking for I can actually find. I'm once again seeing that if I'm using acoustic models trained on timid, it doesn't work very well, and once I get two models that are trained on singing, again that helps. And the F1 measure at my current state of the my state of the art, my personal state of the art, is right now 0.5, which probably isn't usable yet for anything practical, but at least it's improved. And yes, I have an idea how to do keyword spotting in singing. And something that I thought was also interesting is that it depends very much on what keyword you're looking for. So out of those keywords that I showed you earlier, love actually works best. I think that has a lot to do with the frequency of the keyword in my data set. So love occurs very frequently, and in general, using this approach, it's pretty easy to generate a high recall. High precision is more difficult. So if I have something that occurs frequently, then that'll automatically make the F1 a bit better in the end. And then outside of that, you can see this general trend that the fewer keywords I have, the harder the recognition gets, as you can imagine. So something with just two, the fewer phonemes I have. So something with just two phonemes like eyes, that's very hard to recognize, because you can confuse it with so many other things. And you just have the chance of recognizing those two phonemes, and if one of those goes wrong, then you won't find the keyword. And then just very quickly, I just mentioned that in singing I can take phoneme durations into account. I actually tried that out, and it turns out it's not quite true. So what I just mentioned was that it's usually easy to get a high recall. So what I did then was to try out different methods to filter out all of the results that don't make any sense if I have this high recall, so basically improving the precision afterwards. And I tried out these two different approaches, and this is actually a pretty simple approach, which is called post-processor duration modeling, and that means I just I set my parameters to generate a high recall on my data set, and then I actually just go through all of the results and filter out any of those that have phoneme durations that don't make any sense. And it turns out that this does improve the result in the end, so maybe that's also something to explore further. And I tried this out for all of the phonemes, or maybe just for the consonants, because consonants have more solid durations, but doesn't seem to make a big difference. But yeah, so maybe duration modeling does make sense in some configurations. Okay, so those were the first 3 tasks that I've been working on. And what I've been doing recently is more lyrics to singing alignment, because that actually works pretty well at the moment, and you could probably, as opposed to the other 2 tasks, you could actually use this for practical applications. So this is again a state of the art, and I didn't even have to write this myself because there's been some work done on this. There's actually some work on lyrics to singing alignment, which is good to see. Yeah, I'm not going to talk about many details here. So again, I used a fairly straightforward approach for this, and this is more or less what I already showed you earlier when I told you about what I did with the DAMP data set. So I've got my audio data, I've got my text lyrics, and then using acoustic models that I've trained on something before, I do my automatic alignment. So most of the time I'm using acoustic models that are really just trained on Timothy, and that works well enough. But I've also tried it with the newer models that I have, and that makes it a little bit better. And I'm just going to show you a different example. So this one actually was an example of my automatic alignment already, but I'm just going to show you one where I've just been interested in aligning lyrics, the lines of the lyrics to the singing, which is a bit easier to do than aligning the phone. Well, I mean, you'd have to align the phonemes anyway, but it doesn't have to be as exact as aligning phonemes. And yeah, you can look on the bottom right again for the line of lyrics, and you might know the song. Yeah, okay. Unless you want to hear more of this. So, and I specifically picked an example where it didn't work perfectly, but you maybe noticed that it made a mistake back there, but then it caught back up again, so it got back into the rhythm of it. And I also like this one because she doesn't have the clearest pronunciation, but the system is still able to find the correct lines of lyrics. Okay, so this is what it looks like at the moment. And then I tried to think of different applications of this, what you could do with this. And one thing that I presented at this year's Interspeech was this idea that you could maybe search for lyrics based on a singing input, which surprisingly no one has done before. So again, how this works is that I've got my singing recording, and then I do my phoneme recognition on that. And at the same time, I have a set of text lyrics, so it's really just text. I then generate some sort of phoneme template on that, and then I compare my phoneme posteriogram to all of those templates. And the way I did that was by using a sort of modified dynamic time warping approach. It has to be modified because I, for example, don't want to punish if a phoneme goes on for very long, because someone might just really be singing ah, And if I'm just using the text lyrics as input, I don't have any information about the duration at that point. So this is what that could look like. So that again is a phoneme postereogram that comes out of my acoustic model. This could be a phoneme template, which is binary, so it's a one-hot representation. And then I can do my similarity calculation on that and then find a warping path through that. And I can't really demonstrate this very nicely, but it turns out that that actually works. So these are the results if I'm doing that on the whole song. I've just split this up into the female and male test set here because there seem to be some differences. And yeah, so if I'm interested in just the very best result that I get out of my whole data set, so that's the one best result, I can actually reach almost, I think that's almost 90%. And then if I say I'm just interested in the 10 best, and then maybe I can let the user pick which of these 10 songs they were looking for, then I can actually get beyond 90% there. And I had a look at those. I think there are 8% missing. So I had a look at that, and it turns out that in my test set, those are actually songs where something went wrong. So someone actually didn't sing the lyrics or something like that. So that seems to work pretty well. Then one other thing I thought of, I don't know if someone's seen this before, but I did this at the Hammer Hackathon this year. And the idea was that you can actually search for phrases in a song by the lyrics. And the song I picked for that is Bohemian Rhapsody. And I did the same lyrics alignment that I showed you earlier on Bohemian Rhapsody. Used the alignments to split that song up into the lyrical phrases. And then I now have a bot on my phone. I don't know if anyone's using Telegram, so that's sort of like WhatsApp, but I have this bot here. And I can send a word from Bohemian Rhapsody to this bot. And I'll just send it reality, for example. Unfortunately, you can't see this, you just have to trust me. So this bot just replied to me with the line, "No escape from reality," and it also sent me the audio snippet.
No escape from reality.
Okay, so that was just that was just a fun application of that I tried out. And then maybe one last thing that I think could also be a very interesting application, which is automatically removing bad words in songs, expletives. And again, I did this by generating automatic alignments of lyrics to singing. And then once I know where the lyrics occur, I can find out where the expletives occur. So I know exactly where they are, and then I can use that information to bleep them or remove them. This was actually done on a data set that someone here made. I got it from Matthias Mau, so you probably have this data set somewhere here, and I'm just gonna open this example. Okay, let's see. Okay, so I'm first going to play a bit of the original audio. Yeah, maybe from here. So, and I've just displayed the expletives here in this case. Okay, so this was detected automatically, and now if I want to play this on the radio, then I could remove that. And sorry. I can't scroll here for some reason. I could remove that, and for this example I just did that by doing stereo subtraction, and since it's just a short word, it seems to work well enough. Okay, or if maybe for some reason the stereo subtraction doesn't work enough, I thought I could also have some fun with this, and I did this. You can just use a bleep or something. Okay, yeah, I have more examples of these if you're interested in that, so I thought that could be an application of all of this. Okay, so I'm almost done. I'm just going to give a quick conclusion. So in general, I still think phoneme recognition on singing is a bottleneck, and there are probably ways to make better models for this, and that's actually what I'm working on more at the moment, because I think that's what everything else is based on. The language identification at the moment works okay. You could probably use this for some sort of practical applications. Depends very much on what languages you're looking at, and also how long the phrases you're looking at are. So the more data you have, the better it's going to work. Keyword spotting, I think, isn't at the point yet where you could actually use it for something, but maybe you could already use those results to help other systems find information. So I'm thinking of something like mood recognition in music, where you could just try to search for specific keywords, and maybe if it finds some wrong keywords, it doesn't matter so much, but if it finds something like hate, 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 or something, then it might be a metal song. That's what I'm thinking of. And the main problem seems to be that, especially in songs, we're interested in keywords with very few phonemes, and that's something that even ASR people don't really like to do. And then the lyrics to singing alignment already works pretty well, in my opinion, and it even, as you saw, works pretty well on polyphonic data, depending on what you're interested in. So I probably wouldn't use it on a phoneme level, but at least on a phrase level, that actually works very nicely. I think something that I've been noticing across all of those tasks, what seem to be the problems are instrumental solos, if you have background music, or other sorts of background music, but solos are the big problem. Then the results are obviously always very dependent on the pronunciation that people have and on specific accents. And then the one problem that I guess a lot of people in this room also have is that there's not a lot of reliable training and test material for this, which is also something I'm still working on. Okay, so for future tasks, I have a lot of ideas what else could be done. So as I mentioned, right now I'm working on better phoneme models. I didn't talk about my machine learning approaches here very much, and that's because there's nothing fancy going on at the moment. So right now I'm trying out fancier approaches. But yeah, that also depends very much on the data that's available and on the computing power. As I said, most of these things were done on pure singing without any background music. So one obvious next step would be to make it work for polyphonic music in some way. Maybe do source separation, I don't know. Maybe that introduces too many artifacts, but other people probably know this better than me. What you could at least do would be to do some sort of singing activity detections to get around this problem with instrumental solos, or even just segments where no one is singing. So if you don't have to look at those, that will already help you a lot when you're trying to do one of these ASR tasks. I haven't really done any language modeling so far, so if you want to do something like full transcription, then it would also be interesting to look at language modeling for singing. And as far as I know, not a lot of work has been done on that part either, so wide open field. The results of this could be improved to, could be used to improve other MIR algorithms. So I just mentioned this genre or mood classification tasks, for example, or even what I mentioned at the very beginning, this problem where you want to find out where a song is from, and you could exploit the language for that. And then, yeah, I think there's just so many more tasks where you could use this. And I've just listed a couple of those here. So these were just ideas that I had in the last couple of months. So I think you could, for example, do with some sort of cover song detection by looking at the phonemes in a song. You wouldn't even have to know the exact words. You could just go by the phonemes. Could do some sort of lyrical fingerprinting, and you could use that to retrieve lyrics like I just showed you, but maybe on larger databases or even from the internet. You could use it to enhance the fingerprinting approaches that already exist, or query by humming approaches, that sort of thing. I just mentioned this idea that maybe you could use keywords to improve mood or genre classification, or use the language to improve regional classification. You could do some sort of lyrical similarity search or lyrics recommendation. Or you could even just go the other way around and do some sort of singing generation. So I guess everyone has seen Google's WaveNet. You could probably do something like that for singing as well, which would be very interesting. And that's it. These are just my references. And thank you very much for your interest in this.